This video, I'm going to talk a little bit about vectors and vector addition and vector subtraction specifically. Might also get into some vector graphing. So let's go ahead and talk about the idea of a vector. A vector is usually in the form of u, and it usually has an arrow over it like this, is equal to u1 I. You might have a hat over it, or it might be in italics or something like that. I'll talk about what the hat means later. Plus u2j, and you might have a u3k. Ij and k are unit vectors, meaning that they have a length of 1, and they're in the direction of the positive x-axis, the positive y-axis, and if you have a three-dimensional vector, k is in the direction of the positive z-axis. We can write vector u in component form like so, and that's helpful to us sometimes. But I'm just going to be dealing mostly with two-dimensional vectors here. So I'm going to get rid of this k component, and I'm going to deal with u1, u2, like so. And let's say that I have another vector here, v, that is v1 I plus v2j, which is v1, v2. And let's say that I want to add the vectors u and v together. Before we do that, let's talk about some fundamental things here, that there is such a thing as the zero vector. That's 0, 0. So if I would add the zero vector to any vector, I'd get the original vector like that, because if I would, and there is such a thing as a unit vector that we'll get to in a second. That's what these things are with the hats over them. But that'll take a little bit of additional explanation here. Let's talk about vector addition now. U plus V is equal to, in component form, U1 plus V1, U2 plus V2. So we just add the like terms, we add the like components. As you might expect, if I subtract, take a -1 times a vector, just say -1 times that, we can have scalar multiplication. Let's just talk about scalar multiplication in general here. That a scalar multiple c times a vector is going to be c times u1, c times u2. So specifically, if I have -1 times the vector, this is going to be the same distance but going in the opposite direction of u. It's going to be a -u1 and a -u2. So if I want to subtract vectors, just like with scalars, I'm really adding the opposite. So this is going to be u1, u2 plus a -v1, -v2 is equal to u1 minus v1 and u2 minus v2. All right, we've already done scalar multiplication. So let's talk about this idea of the magnitude of a vector. You may get single bars around it that look like absolute value bars. You may get double bars around it. Either way, it's the magnitude of the vector. We're going to take the square root of each component squared, added together. So right now in 2 dimensions, that looks a lot like the Pythagorean theorem and the distance formula because it is. It works this way as well in 3 dimensions. When we get there, we would just add plus a u3 squared. So if I want to force myself to have a vector with a length of 1, then I can take and multiply by the reciprocal of the magnitude of the vector times my vector here, like so. So this becomes, I put a hat over it to show that it's a unit vector. Like so. If I had 3 dimensions, it would work the same way. Right now that you know all those basic operations, let's talk about something else that's interesting. I talked about addition and subtraction there just a second ago, but I didn't talk about multiplication and division because there's actually 2 types of multiplication that we could have with vectors. So we could have something called a dot product or a scalar product. And this is not going to be a vector. When we're done with it, it's going to be a scalar, but I just multiply the first components together and I add them to multiplying the second components together like that. And I just get a number that's a scalar. But I could also have something called a vector product. And the vector product, so this is called the dot product. And it's a scalar product. But I could also have something called the cross product, which is a vector product. And the dot product is going to be helpful to tell us when angles, when vectors are perpendicular to one another or orthogonal to one another, because if u dot v equals 0, then u is perpendicular to or orthogonal to v. They're perpendicular. The cross product here is going to give us a vector that's perpendicular to the plane that defines u and v. You'll get more into that in calculus 3, but if I take u and I take v and I put them head to tail, they make a parallelogram type thing here, which defines a plane, a flat piece of paper, and that this vector that we're going to get u cross v is going to be perpendicular to that coming out of the paper, pointing up, or going out of the paper pointing down. And so we'll figure out rules for how to figure that out later. But for right now, understand that that's what we're trying to do, is get a vector that we know is perpendicular to both vectors u and v. We're going to have to go back to matrices to do that. And so we're going to always have a yeah, we're going to have a three-dimensional vector here. So we're going to have I, J, and K, and we're going to have vector U in row 2. And we're going to have vector V in row 3. And I'm not going to do a lot of this right now, but you can go back to some of the stuff that we talked about with matrices. If you didn't talk about three 3x3 determinants, you can go back and look at that. But I'm going to expand on row 1 here, which is vector I, and then this is U2, U3, V2, V3. Then this is going to be a minus J times U1, U3, V1, V3 plus K times U1, U2, V1, V2. So that's going to give us U2, V3 minus U3, V2, I minus the quantity U1, V3 minus U3, V1, J plus U1, V2 minus U2, V1, K. And I'm just going to distribute this negative here. U2, V3 minus U3, V2, I plus U3, V1 minus U1, V3, J plus U1, V2 minus U2, V1, K. And just suffice that to say that you see that it's a vector that's three-dimensional, and I've shown you that it is orthogonal to both vectors U and V and the plane that's created by them. You won't be doing a lot of this in pre-calculus, but you'll need to know it for physics. We talk about something called the right-hand rule to know whether the vector U cross V is going to point up or down. And there we go. So now one other item that I'd like to mention is that we can use the idea of vectors to help us deal with complex numbers, because complex numbers Z equals A plus BI. I'll just call it Z1 and Z2, A1, B1, A2, and B2, like so. And these are going to obey a lot of the same rules. So I could really look at this like it's a two-dimensional vector, and it's going to obey a lot of the same kinds of rules. So adding vectors together, adding complex numbers together, pretty much the same thing. I'm going to add components together. Subtracting complex numbers. Subtract the components. When it gets to multiplication and division, though, it's a little different, but it's okay because we're going to start to look at this in polar, which is something that we talked about a little bit ago. And I'm going to find R here, and I'm going to say that Z can be written as an RE to the I theta. So let me give you an example here so that you are with me. So if I say something like 3 plus 4i, and I want to look at that like it's out here at 3 on the x, and this is my yi, this is my x, 3, 4, and it's out here. And if I want to imagine this vector that goes out there, that position vector, it makes this right triangle. If this is 3 and this is 4, by the Pythagorean theorem, that's 5. R is going to be 5 here. My theta, and actually let me pick one that I know the angle for from the unit circle. I'm sorry. Those were okay numbers to get an R, but let me pick 1 and the square root of 3 here. So redraw this 1 and square root of 3 like so, and 1 and root 3 by the Pythagorean theorem. This is 2, and that is going to be a 60-degree angle. So theta is pi over 3 radians. So I can rewrite that complex number as 2e to the I times theta. So I'm going to just switch the order there, pi over 3i. Why would I want to do that? Because let's say that I had another one that was, say, 1 plus I. And I know that by the Pythagorean theorem, that's got a radius of square root of 2, and the angle is pi over 4. Now let's say I wanted to find z1 times z2. That would be really hard to do in rectangular. I'd have to FOIL, and I'd have to keep track of all my real parts and my imaginary parts, but I don't have to do that with this. This is just going to be R1 times R2 and e to the I times theta 1 plus theta 2, because when we multiply like bases, we add the exponents. So in this case here, this is going to be 2 root 2 e to the I times pi over 3 plus pi over 4 is 7 pi over 12. So this is 2 root 2 e to the 7 pi over 12 I. So I could come back here and could say, okay, if I wanted to graph z1 times z2, I go to 7 pi over 12, which is just a little bit past pi over 2, and I'm going to get a longer vector there that's not going to be 2, and it's not going to be root 2, it's going to be 2 times root 2, and that's where z1 times z2 is going to be located. I can do the same kind of thing with division, only when I divide, I like bases, I subtract the exponents, but I think you get the idea. Okay, I'm going to stop here. I don't have any example problems for this. I'm just talking about this for the sake of physics. I did forget one thing. Hang on. So I want to show you one other form that's important, not only for physics, but for differential equations. So I told you already that this is e to the I theta. Well, e to the I theta can also be written as cosine of theta plus I sine of theta. So that's going to be important later, and you might be doing quite a bit of that in physics as well as in differential equations, where you'll be talking about things in terms of sine and cosine. And the imaginary part will be the part with the sine function usually. Okay, that's it for general overview of vectors, which we do not cover in depth in pre-calculus, the school where I work. I wanted to throw a little bit of this on the website to help those of you who are needing it for physics, especially university physics, and for those who need a little review before you go into a Calculus 3 course or a linear algebra course where you also talk about vectors, but you talk about them in terms of matrices. So that's another aspect we aren't going to talk about here, but they are related topics. So that's it for now. Have a good day.